Okay, statistics class, welcome to week 4 of your distance learning. Hopefully all is going well. We want to continue on our thoughts regarding regression here. And we're going to look at 2 new examples. We're going to do 4 together, and then you're going to do 4 on your own, and that will be your week's work. In this situation, it says the following data shows the mean temperature of the week and the corresponding heat bill. Determine if you should use linear, logarithmic, or exponential regression to model this data. Also determine the R value, best fit equation, expected heating bill if the mean temperature was 55 degrees. So you can, we'll talk about the exponential and the logarithmic regression here in a little bit. But if we just simply, wonder if there's a relationship among the data. Again, that's our question. Is there a relationship among the data? Sometimes the best thing to do is just go ahead, insert a chart. And again, we hope that it chooses a scatter plot. We can see what it chooses. It does choose a scatter plot, and you want to look at that data. Does it look like the data has a certain trend to it? Does it look like it kind of makes a line? And in this situation, I would say, yeah, it does. It really does. So I would say that because it looks like it makes a line, you have linear regression. And so as you go into your edit chart here, and it looks like I've got to continue to do this. Looks like that's going to be a good spot for me today. Click on the chart and then drag it on over. Very good. As we go on to customize that chart, if you simply go into, again, series, what we can do is we can choose to add a trend line. And as we add the trend line, you can see that the type is linear. Our label, we are going to use our equation, and we are going to show R squared as well. So that will allow me to answer some of these questions here. It says, determine if you should use linear. We used linear. It makes a line. Determine the R value. R is equal to, looks like I have to take the square root of 0.746. And so we use, what did I choose to use? Scientific Desmos. And I think that scientific calculator and Desmos usually turns out pretty good. Square root of 0.746. So I'm going to go ahead and try that. Square root of 0.746. And you can see I get a 0.8637. So I'm just going to go 0.86 on that. 0.86. Is it positive or negative? Well, you can see that the trend line is heading down and that there's a negative slope. So therefore, our R value should also be negative. So I'm going to go back in here and insert a negative value there. So R is negative. It says after the R value, the best fit line equation. I'm going to make a little bit more room here by expanding my cells. Let's see here. So we've got a heating bill is equal to negative 1.68 times X. In this case, X is our mean temperature. So I'll do T for temperature plus 149. So there we have the expected, or the equation we use for the best fit line. And finally, it says, what's the expected heating bill if the mean temperature was 55 degrees? So we just take negative 1.68 times 55, plug it into our equation. Negative 1.68 times 55 plus, we got a plus 149. And we've got 56.6 is the result. And so if I go back over here, I get heating bill is equal to $56.6. And that makes sense because it looks like that there's an inverse relationship. It looks like as the temperature increases, the heating bill decreases. So if I have a temperature of 55, which is larger than what I have in the other example or other sets, that it should go down. In fact, $56.60, it does go down. Let's look at some mortgage stuff here. Okay, similar type of question. It says following data shows the monthly mortgage payment of a corresponding income. So if somebody makes $2,030 a month, then their corresponding mortgage payment might be, say, $1,200. We'll see how that works out. Determine if you should use linear, logarithmic, or exponential regression to model this data. R value, best fit equation, expected income if the mortgage was $1,200. So let's first see if there's a relationship among this data. I grab it and I go insert chart. And it does come up with a nice scatter plot. I'm going to try to drag that scatter plot over here and make it a little bit smaller. Grab the corner, make it a little bit smaller. And does it look like there's a relationship? Yeah, it does. It looks like that there's a positive or a direct relationship here. I'm going to go ahead and edit this chart. I'm going to customize it. And in my series, I'm going to add those pieces that we talked about, which would be a trend line. And I'm going to, it is linear. It looks like it makes a line. The label, I'm going to use equation and show R squared. Now I have all that data, I can answer the question. It is linear. Determine the R value. I have to take the square root of 0.948. Looks like there's a strong relationship. 0.9, that's pretty high for an R squared value. So we take the square root of 0.948. Go to my calculator, square root 0.948. I get 0.97. So we're going to say R is equal to 0.97, and it is positive. The line is going up, so I leave the R value positive. Best fit equation, we have mortgage is equal to 0.405 times X, in this case, X is income, I for income, plus 178. Make a little bit more space here just so we can see it. So I've got my best fit equation. And now it says, determine the expected income if the mortgage was $2,100. So I'm going to go to the board for this one. Again, it says the mortgage was $2,100. So $2,100 goes in for mortgage is equal to 0.405 times your income plus 178. So I'm going to go ahead and take my calculator here, turn it on, and I do 2,100. I subtract 178, and I get 1,922. 1,922 is equal to 0.405 times your income. Now I have to divide both sides by 0.405. Divide by 0.405, and we get $4,745. If you want to push a mortgage payment all the way up to $2,100 a month, you got to be making more money a month. And that would be $4,745. $4,745. There we go. There's two examples of linear regression, things you've seen before. Let's look at a little bit different situation here. Okay, rabbits. Following data shows the number of years the rabbit population in park reserve. So we have determine if you should use linear, logarithmic, exponential regression. Determine the R value, best fit equation, expected rabbit population after 10 years. So is there a relationship? Well, it looks like as the number of years increase, the numbers of rabbits increase. And in fact, it looks like that they're increasing a little bit more dramatically. And so if we insert a chart here, you can see that we get this type of shape. And if you get that kind of a curve, and this might look familiar to you because, especially at this time we're dealing with COVID-19, this is kind of how things in nature sometimes grow. They grow exponentially. When you get something that looks like a curve, that it's trending like that, and you expect that there's multiple growth, that things are building upon each other, that's a key that we want to say that there's probably exponential growth here. So it really looks like instead of using linear, it looks like we should use exponential. So in our series, we do choose to add a trend line, but you see the line doesn't fit very well. So type, instead of linear, choose exponential. And it looks like the exponential equation actually fits really, really well. There's a few things we can do with that. Number one, you want to add a label. So it says use equation. And then also show your R squared value. Look at our R value is 0.99. I'm going to close that off and be able to make my workout, put my work up here. So is it linear, logarithmic, or exponential? It is exponential. And what we would like to is have an R value. R is equal to, I have to do the square root of 0.99. And so if I do square root of 0.99, I get 0.99. So it looks like there's a very strong relationship going on here. A 0.99 value is really good. So we've got that. It also says that we should determine the best fit equation. So it looks like number of rabbits is equal to, this is where it's a little bit different, folks. It says 11.6 times E. E is a number, and I'm going to write it on the board here in a second. E raised to the, and to show raised to the, you use a caret key. It's shift 6. 0.553x. And there we have it. I'm going to write that up on the board so you can understand what that is. E is a special number that we use in growth situations like this. Here we have rabbits. And E is a number that occurs in nature. We say it's 2.718. So kind of like pi is 3.14. So it says that rabbits is equal to 11.6 times E, and it's raised to the 0.553x. And so you could just type in R is equal to 11.6 times 2.718 raised to the 0.553. And then you got to plug something in for X. And this situation says, what would be after 10 years? So that's what you want to plug into your calculator. And as I go ahead and type that into my calculator, if you want to use one of these instead, you could see that in this situation, E, well, you could just type in 2.718. So 11.6 times, parentheses, 2.718 raised to the, you use this caret key right here, raised to the, and then I like to always put whatever I'm raising it to in parentheses, so make sure it does that by itself. So 0.553 times 10. So you can see here what I have written into my calculator. Let's see if we can get that to show up. There you go. And that should be able to give me what I need. Press enter, and it looks like 2,923 rabbits. There we have it. Last example, we're going to look at weightlifting and bench press. It says the following data shows the max bench press of an athlete in the corresponding number of years they've been weightlifting. So determine you should use linear, logarithmic, exponential data in order to model this. So let's see if there's a relationship. Looks like the bench press starts off rather weak at 80 pounds, then jumps up to 125, but it looks like it kind of tapers off at the end. So if we insert a chart here, we can see that the chart that it produces, it is not so much a line, but more of a curve that kind of tails off. And if you end up with a curve that kind of tails off, that is what we refer to as logarithmic regression. So I'm going to put those kind of three options up on the board for you right now so you can see. That's linear. That's exponential. And that's logarithmic. Those are the type of shapes that they make. And so looking at the data, you could kind of figure it out that if you're doing something like weightlifting, you might start off, increasing a lot right away, but eventually you kind of taper off. So logarithmic is a really good option here. So we're going to customize. We're going to go into our series. We're going to go ahead and add a trend line. We're going to choose, instead of linear, we're going to choose logarithmic. And our label, we're going to choose as using an equation and show R squared. So for r squared, we're going to answer that question first. Which logarithmic option did, or which regression option did we use? Logarithmic.